In DHCP spoofing attacks, the attacker places a rogue DHCP server on the network. There are two main features of the DHCP mechanism that emerges the DHCP spoofing attack. First, there's no authentication process and priority in the DHCP mechanism. Second, as clients are turned on and request an address, the server with the fastest response is used. So if the device receives a response from the rogue server first, the rogue server can assign any address as well as control which device it uses as a gateway. So a well-designed attack can funnel traffic from local hosts to a rogue server that logs all the traffic and then forwards that traffic out to the correct gateway to the device. And this action would be almost transparent, right? Thus, the attacker can steal information pretty much invisibly. How are you going to find that? That's why you're here. Let me clue you in on another important point. While setting up a rogue DHCP server, we cannot be so sure whether the client received the settings of the rogue server or the legitimate server. That's why it's way better to use the DHCP spoofing attack with a DHCP starvation attack. All right? In a DHCP starvation attack, an attacker broadcasts a large number of DHCP request messages with spoofed source MAC addresses. If the legitimate DHCP server in the network starts responding to all these bogus DHCP request messages, available IP addresses in the DHCP server scope will be depleted within a very short span of time. Now, once the available number of IP addresses in the DHCP server is depleted, network attackers can then set up a rogue DHCP server and respond to new DHCP requests from the network DHCP clients. By setting up a rogue DHCP server, the attacker can now launch a whole DHCP spoofing attack. So here is how we can perform a DHCP spoof attack together with DHCP starvation attack. So we'll create a lot of DHCP discovery packets to request new IP addresses from the DHCP server. DHCP server replies to these requests. IP address space is limited. For example, a Class C subnet has about 250 IP addresses available. So since the IP addresses are used for fake MAC addresses, there aren't any more IP addresses for legitimate clients. DHCP cannot respond to the new requests, and the clients which cannot have IP addresses become out of service. So now we'll set up a rogue DHCP server, which is the only server to respond to the client's IP address requests right now. The rogue DHCP server starts distributing IP addresses and other TCP/IP configuration settings to the network DHCP clients. TCP/IP configuration settings include default gateway and DNS server IP addresses. So now we can replace the original legitimate default gateway IP address and DNS server IP address with our own IP address. Once the default gateway IP address of the network devices are changed, the network clients start sending the traffic destined to outside networks to the attacker's computer. The attacker can now capture sensitive user data and launch a man-in-the-middle attack. So let's see how we can perform a DHCP starvation attack and consume the DHCP pool using Yersinia. Yersinia is a network tool designed to take advantage of some weaknesses in different network protocols. The protocols currently implemented in Yersinia are shown in the slide. Now we're going to use our VMs in NAT mode during this demo. So I'm on my host machine and open the virtual machine library. This is the Kali that I'll use. So click this icon to see the VM settings. Click the network adapter icon. It says Internet is shared with my Mac, so if you look at the explanation in the right-hand side of the frame, it means the VM is in NAT mode. So this is what we want, so just leave it as it is. The Connect network adapter is selected, so Kali is ready to use with the NAT network connection. So Windows 8 is the other VM that I'll use to demonstrate DHCP starvation attack. Let's have a look at the network settings of Windows as well. Yeah, it's in NAT mode, and the network adapter is connected. So I'll disconnect the network adapter by clicking here, because I just want to show you that the DHCP of VMware is working properly. So I want to add a second network interface for my Windows system. Click Show All and go to the Settings menu and click on Add Device at the upper left-hand corner. Select Network Adapter and click Add. The details of the new adapter are listed here. The NAT mode is selected by default already. So uncheck the Connect Network Adapter box for now. Okay, so as you see, we have two network adapters for the Windows system. Both of them are in NAT mode and are disconnected. So now I'll start the Windows 8 system. Log in, and sure enough, it's ready. Right-click on the network icon at the lower right corner and select Open Network and Sharing Center. And right there, we don't have an active network at the moment. That's to be expected. So now I connect the first adapter and activate the network. In VMware Fusion, you can see and change the setting in several ways. If you use the VM in full screen mode like I do, just go to the upper side for VMware Fusion menu. There it is. And if the menu does not appear, just press Command-Control buttons together. Right, so this is the default setting of VMware Fusion to turn back to the host system when you're inside a VM. And these are the network adapters. When you click on them, you'll see the short menu for network adapter. And here you can connect or disconnect the network adapter, change the network mode, NAT bridge, or host only, and you can use this pop-up for the network adapter settings. Now, the second way to see and change the network settings is to click the settings icon. Then select the adapter to see the settings. So the third way is to go to the virtual machine menu. Go to the network adapter, and you'll see the short menu of the adapter. Now go to the first network adapter icon and click on the Connect Network Adapter menu item. And now you see in the Network and Sharing Center window, we now have an active network connection. So click the network name and the Details button. Here are the connection details, and right there it is. DHCP is 172.16.99.254, and it assigned an IP address for the VM 172.16.99.221, as well as the gateway and the DNS address. Now I'll go back to Kali and open a terminal screen. Using the ifconfig command to see the network interface configuration, and sure enough, it has the IP address. So ping the Windows 8 system to validate the network, 221. Okay, we receive the ICMP reply, so everything looks okay. Now is the time for Yersinia. So type man Yersinia and hit enter to see the manual. And right here in the manual, Yersinia is a framework for performing Layer 2 attacks. And here's a list of protocols implemented in Yersinia. Scroll down, you'll see the options. We can use uppercase G to start a graphical interface. So let's go ahead and use it in graphical mode. You can press Q to quit from the manual and turn back to the terminal. Now type Yersinia, uppercase G, and press Enter. So this is the graphical user interface of Yersinia. Before running the attack, let's open Wireshark and monitor the network packets to see what happens when we start the attack. You can type Wireshark in terminal to start it, or just click the Wireshark icon. To select the interface to listen, double-click ETH0. And to discard the different packets and focus only on the DHCP packets, we can filter the packets. In the filter box, type bootp and hit enter. So bootp is the short form of Bootstrap Protocol, which I mentioned earlier. It's basically a computer networking protocol to automatically assign an IP address to network devices from a configuration server. And obviously, it's used by the DHCP server. Now we can turn back to Yersinia and prepare and run the attack. So click Launch Attack. That's the link at the upper left-hand corner. The tabs in the window are the implemented protocols. Choose DHCP and select Sending Discover Packet. Now click OK. As soon as we click the button, Yersinia starts sending dozens of DHCP requests in a second. It'll keep sending the packets till we stop the attack. Now look at the Wireshark window. These are the DHCP Discover packets sent by Yersinia. So now, while Yersinia is sending the DHCP Discover packets, let's activate the second interface of the Windows VM. And let's see if the DHCP server assigns an IP address for the second interface. All right, so we're in the Windows VM now. Go to the second network adapter, click Connect Network Adapter 2 to activate the second interface. Now, do you remember what happened when we activated the first interface? We saw the new network activated, but now there's still no network because the DHCP server is busy replying to the request created by Yersinia. It's not going to answer the Windows 8 second interface. So let's turn back to Kali and stop the attack. In Yersinia's interface, just click List Attacks, and then click Stop or Stop All. In the Wireshark window, look at the bottom of the packets list. We now have a complete DHCP sequence. Discover, Offer, Request, and ACK packets. In the Windows 8 VM, we now have the second network. The first one was Ethernet 02. This one is Ethernet 0. Click on it. In the status window, click on Details. The second interface has an IP address now, assigned by the DHCP server. Now, to be honest, there are a number of different types of VLAN attacks in modern switch networks. The VLAN architecture simplifies network maintenance and improves performance, but it also opens the door to abuse. So it's important to understand the general methodology behind these attacks and the primary approaches to mitigate them. VLAN hopping enables traffic from one VLAN to be seen by another VLAN. Sounds kind of fun, huh? So as we've already seen before, a virtual local area network, virtual LAN or VLAN, is a group of hosts with a common set of requirements, which communicate as if they were attached to the same broadcast domain, regardless of their physical location. VLANs work by applying tags to network packets and handling these tags in networking systems, creating the appearance and functionality of network traffic that is physically on a single network, but acts as if it is split between separate networks. Capiche? So let's take a moment and remember the reasons of why we're using VLANs. Security. Groups that have sensitive data are separated from the rest of the network. Cost reduction. Cost savings result from less of a need for expensive network upgrades. Higher performance. The number of router hops reduces and the apparent bandwidth for network users increases. Broadcast storm mitigation. Every VLAN only receives its own broadcast packets. Improved IT staff efficiency. As we were talking about before, VLANs make it easier to manage the network. It also simplifies the company's management. So here are the basic principles of the switch ports. The ports of a switch is in dynamic desirable mode by default. If the device connected to the port is a computer, The mode of the port becomes access, and the port is dedicated to that computer. If the device is another switch, the mode of the port becomes trunk. So by default, trunk ports have access to all VLANs and pass traffic for multiple VLANs across the same physical link, generally between switches. So switch spoofing is a type of VLAN hopping attack that works by taking advantage of an incorrectly configured trunk port. In a switch spoofing attack, the network attacker configures a system to spoof itself as a switch. So this spoofing requires that the network attacker be capable of emulating 802.1q and DTP messages. By tricking a switch into thinking that another switch is attempting to form a trunk, an attacker can gain access to all the VLANs allowed on the trunk port. So the best way to prevent a basic switch spoofing attack is to turn off trunking on all ports, except the ones that specifically require trunking. On the required trunking ports, disable DTP, Dynamic Trunking Protocol, and manually enable trunking. Another type of VLAN hopping attack is known as double tagging attack. This type of attack takes advantage of the way that hardware on most switches operates. Most switches perform only one level of 802.1q de-encapsulation, which allows an attacker to embed a hidden 802.1q tag inside the frame. This tag allows the frame to be forwarded to a VLAN that the original 802.1q tag did not specify. An important characteristic of the double tagging VLAN hopping attack is that it works even if trunk ports are disabled, because a host typically sends a frame on a segment that is not a trunk link. So let's see how the double tagging VLAN hopping attack is performed step by step. The attacker sends a double-tagged 802.1q frame to the switch. The outer header has the VLAN tag of the attacker, which is the same as a native VLAN of the trunk port. Normally, a switch port configured as a trunk port sends and receives VLAN-tagged Ethernet frames. Native VLAN is the only VLAN which is not tagged in a trunk. In other words, native VLAN frames are transmitted untagged. The assumption here is that the switch processes the frame received from the attacker as if it were on a trunk port. In this example, the native VLAN is VLAN 1. The inner tag is the victim VLAN. In this case, it's VLAN 20. The frame arrives on the switch, which looks at the first 4-byte 802.1q tag. The switch sees that the frame is destined for VLAN 1, which is a native VLAN. The switch forwards the packet out on all VLAN 1 ports after stripping the VLAN 1 tag. On the trunk port, the VLAN 1 tag is stripped, and the packet is not retagged because it's part of the native VLAN. At this point, the VLAN 20 tag is still intact, and it has not been inspected by the first switch. The second switch looks only at the inner 802.1q tag that the attacker sent and sees that the frame is destined for VLAN 20, the target VLAN. The second switch sends the frame onto the victim port or floods it, depending on whether there is an existing MAC address table entry for the victim's host. So the best approach to mitigating double tagging attacks is to ensure that the native VLAN of the trunk ports is different from the VLAN of any user ports, right? In other words, do not let the users use the native VLAN. In fact, it's considered a security best practice to use a fixed VLAN that is distinct from all user VLANs in the switch network as the native VLAN for all 802.1q trunks.